And well, thank you all for being here. I recognize that it's going to be very difficult to basically reach the quality level of the previous speakers, but in case you get bored, just think about the prize draw at the end. So I'm going to try to make it reasonably interesting. So this talk is, despite the title, is really about harmonic load pool. I'm going to start with a comparison. I'll try to be neutral. A technical comparison about the different harmonic load pool solutions that we have today. And then I'll give some examples of how some of our customers, in this case the Fraunhofer Institute for Applied Solid State Physics, use these types of harmonic load pool measurements to basically characterize their gallium nitride technology. So it's not really about PA design, to the disappointment of Professor Cripps. It's also not about behavioral models, at least not this time. So this is the outline of my talk. After a brief introduction, I'll give an overview of the different available load pool techniques. I'll then describe into just a little bit more detail our mixed signal active harmonic load pool system, because this is the system that has been used for the harmonic load pool examples that I'll describe in the next session. And I'll present both measurements at S-band and at X-band, and then finally some conclusions. So as I'm sure that all of you in this room are aware of, load pool is essentially the technique where you can vary the impedance at the output of the device under test and measure all the performance parameters of the transistor, such as output power, efficiency, and so on. And through these measurements, you can basically determine what the best matching is for your application. Obviously, this technique has been around for a while. When we look at the different tuning techniques that we have today, there's mainly two. Industry's workhorse has been, of course, passive mechanical tuners. A tuner is a very simple element, an airline with metallic probe or slug that can move in the X and Y direction. And by getting closer to the airline, it can interrupt the electrical field and basically create the reflection. So by moving in the Y and X, this tuner moves and can tune any impedance. The tuner is a passive element, so the reflection will always be smaller than the wave coming out of your device under test. This means that if we look at this formula, basically your gamma, the maximum gamma that you can provide to the device, it's limited by the losses of the tuner and of all the interconnects. And here you find some numbers, just to give an idea when you look at tuner manufacturer specifications, what you can achieve in terms of gamma and impedance. You can use passive mechanical tuners to do harmonic tuning. In this case, you cascade either 2 or 3 tuners to tune fundamental, second, and third, or you can have tuners with multiple carriages inside the tuner. Basically, the 2 degrees of freedom or the 3 degrees of freedom allow you to tune the impedance not only at fundamental but also second and third harmonic. And even though these are strictly related, meaning that one carriage will move the impedance also at the harmonic, for example, through software you can basically characterize your tuner and tune the 3 frequencies independently. Active tuning, it's becoming more and more popular in the recent days, mainly because of the problem of the losses in tuners. The concept is pretty straightforward. Your gamma is defined as the ratio of 2 waves. In an active tuner, you can essentially create an arbitrary A2 wave. By moving its amplitude and phase, you can create any reflection coefficient that you desire. You have an amplifier here, so in principle you can achieve any gamma, even bigger than unity. And harmonic tuning, it's fairly straightforward with active tuners. You have a frequency multiplexer, and by having multiple signal generators, you can tune 2 or 3 frequencies independently, completely independently. So when I compare the two solutions, the big advantage of a mechanical tuner is that it's very simple to understand and to use, and it's normally the preferred choice for very high power measurements because of its high power handling. The gamma, the maximum gamma that you can reach, it's the same at 1 watt or at 500 watt. Big disadvantage is the losses. And the fact that you have to cascade multiple tuners or multiple carriages for doing harmonic tuning, it's an even bigger problem when doing harmonic tuning because your losses increase. As Professor keeps mentioning in his talk, it's slow because it has to physically move. And the electrical delay, that's a problem that I'll talk a little bit more later. It limits the maximum bandwidth of the signals, the modulated signals that you can use. On the other hand, tuners have high gamma, active tuners have high gamma, and they're about 3 to 5 times faster than a mechanical tuner. With some implementations, as in the mixed signal, they're even maybe 100 times faster. Modulation, it's only possible with mixed signal active load pool. In general, not possible with conventional signal generators based systems. One of the drawbacks is that you do need multiple signal generators to control the harmonic. So these type of systems can become costly when you want to control 3 harmonics. And probably the biggest drawback, at least to my opinion, is the fact that you need a big high power amplifier when you want to characterize extremely high power transistor. So just to give a rough rule of thumb, you normally need an amplifier that's at least 2 times bigger than the output power of your device under test. Nevertheless, we have been using these systems up to 500 watt pulsed. It's just that you need a very big amplifier. The 2 techniques can be combined quite effectively into a hybrid active solution, where basically the big advantage is that the tuner element reflects most of the power and therefore limits or reduces the power needed by this amplifier while maintaining all the advantages of active load pool. Then again, this comes at the price of increasing complexity and possibly cost. So when you look at load pool systems from the system point of view, so not from the tuning element point of view, the traditional way of doing load pool is by basically using power meter or spectrum analyzer to measure output power and the source available power. In this type of systems, your tuning element is placed as close as possible to the device under test to limit the losses that are in your setup. You can see an example of such a system over here. It's normally based on conventional instrumentation, signal generators and power meter, spectrum analyzers. There are a couple of problems with these type of systems, or drawbacks, let's call them drawbacks. Well, you can only measure scalar power. That means you don't have any information on your input gamma or on your input delivered power to your device. So you will know transducer gain, but you will not know power gain. One other potential issue is that the measurements are de-embedded to a DUT reference plane through a characterization of the tuner itself. So the accuracy of your measurement relies on the calibration accuracy of your tuner and on the repeatability of your tuner. So it's very important to have tuners that are reliable. In terms of types of measurements that you can do, you can essentially measure with all types of signals, CW, pulse CW, two-tone modulated signal, but you have to be careful when using modulation to the maximum bandwidth of your signal. And I'll come back to that later. More recently, a preferred way to basically measure power, it's through the use of a VNA or something that looks like a VNA. So in this type of system, also called vector receivers, you normally have couplers placed between the tuning element and your DUT. In this way, you can measure the A and B waves going in and out of your device under test. And from the A and B waves, you can calculate output power, input power. You also have information about input impedance and therefore power gain, and so on. Of course, these couplers need to be very low loss. You have to minimize the losses if you're using passive tuning elements. The main advantage of a system like this is that the fact that you're measuring now a vector quantity allows you to measure actual input delivered power and gamma in, and therefore also measurements like AMPM, PAE, and so on. The measurements are calibrated directly to the DUT reference plane, so there's no calibration required of the tuner itself. At least the accuracy doesn't rely on the calibration of the tuner. And this makes for the most accurate measurements. It's also the type of systems that are normally used when doing active load pool. So with this type of systems, normally, let's say when using conventional vector network analyzer, you're only limited to measurements like CW, pulse CW, and two-tone signals. The good thing now is that you have more quantities. You're able to measure more quantities, things like, as I mentioned, AM, PM, but also time domain voltage and current if you have an MVNA, nonlinear vector network analyzer, or an LSNA. And it's also possible to do behavioral modeling, even whether you believe in it or not, that's for another talk. These are a couple of examples. This is a system that's based on a conventional network analyzer with passive tuners. It can be a hybrid system, which means it can have active tuners as well as passive tuning. This example here is that of a mixed signal active load pool system. So a mixed signal active load pool system is also a vector receiver load pool system. The difference, the main difference between kind of a conventional vector receiver system and this system is that this is a completely turnkey solution. We have a dedicated VNA or MVNA, and we have dedicated signal sources. So the term mixed signal comes from the fact that basically we combine traditional analog techniques with ADC and DACs. But in terms of the tuning element, basically the tuners are low frequency arbitrary waveform generators. The signals are then upconverted to fundamental and harmonic frequencies. So these form the fundamental second and third harmonic tuners, can be both on the load and on the source side. From the measurement point of view, it's a vector receiver system. So you have couplers to measure the A and B waves on your device under test. These signals are down converted to a low frequency, and they are sampled with wideband A to D converters. So the main advantage of this type of system compared to a conventional system is, well, all the advantages of active load pool and vector receiver load pool. But it's also about 100 times faster than a conventional system. I'll give a bit of an overview about that. And it's probably the only system that can measure with a wide modulation bandwidth. And it actually allows to have complete control of your reflection coefficient of your gamma arbitrarily within the modulation bandwidth, so within the 240 megahertz. So I mentioned that there's basically two main advantages, the speed. Basically, thanks to the use of the ADCs and DACs and the fault synchronization between these two, we're able to fit in one single waveform multiple segments. So to try to be a little bit more clear, if you consider this as your input signal and you have two segments with one sine wave with a certain amplitude and another sine wave with a bigger amplitude, you're basically stimulating your device under test with two input powers. When at the same time your load signal is composed of multiple segments with different amplitudes and phases, you are stimulating your device with multiple loads, also within one single waveform. And this can be done, as it is now depicted in this picture, in a kind of in a CW fashion, but it can also be a pulsed CW measurement. This allows you to basically control and measure the gammas and the device performance within one single shot. So this makes it extremely fast. Just to give an example, we have this measurement here on a GaN device where you sweep 13 power levels and 64 load impedances in about 30 seconds. And this can be done not only at fundamental load pool, but also with harmonic source and load pool. So one other advantage of a mixed signal active load pool is the fact that the electrical delay can be cancelled and that you have full control of your impedance in the band. So when I talk about electrical delay, what I mean is that anytime you have a tuner, whether that's passive or active, between your tuner and your device under test, there's a certain physical length. That means that your impedance or your gamma is very well controlled or fixed at the center frequency of your band. When you look at what's happening around the band, you'll have a certain phase delay that depends on your physical length. So this phase delay can go from about 3 degrees per megahertz in very optimized systems to about 30 degrees per megahertz on different types of system. What that means is that essentially your device is seeing something that it's not realistic anymore, and it's not comparable with a final circuit that you would be implementing. So you have to be careful at looking which types of, at trusting your measurements at that point. Now, in a mixed signal active low pool system, we use a relatively simple approach to basically control the gamma versus frequency within the modulation bandwidth. If you look at this diagram, basically, whenever in a measurement system you have a realistic modulated signal, that's going to be a finite sequence in the time domain. So your signal is going to be periodic. Just to give an example, wideband CDMA signal that's according to standard will have about 11,000 tones within a modulation bandwidth that are closely spaced apart of about 1.5 kilohertz. So when you have such a signal in the frequency domain, that's a multi-tone. On the output side, we basically have the ability to measure all the tones composing this signal and to control arbitrarily in amplitude and phase all the tones that are composing this signal. So by adjusting the amplitude and phase of each one of those tones, we can arbitrarily control the gamma at the device reference plane. So since time is a bit short, I will just skip over this. It's just a basic comparison table of the different solutions. Now, no matter what solution you're using, obviously when you provide the same conditions to the device under test, all the different measurement systems need to give you the same answer. So we have done a comparison between these different types of systems that I have described, and essentially you do see the same results on all of them. So I'm going to step now to the few examples of harmonic load pool measurements. These measurements, as I mentioned, have been done by the Fraunhofer Institute of Solid State Applied Physics in Freiburg on their gallium nitride HEM devices. So the objective here, it's not really to design a PA, but it's mainly to characterize the technology and to evaluate through harmonic load pool what the peak PA is that the technology can give. So these experiments have been done both at 2 gigahertz and 8.7 gigahertz. And as I mentioned, all the examples here have been measured with the mixed signal active load pool system, but you could use any harmonic system that can provide the right reflection coefficient to the device under test. So normally when we start with a device that it's completely unknown, the very first thing is to just start with a simple fundamental load pool sweep. In this case, we leave all the harmonic impedances constant at 50 ohm. And here you see basically the measurement results where you have PAE in black and power gain in green. A measurement like this takes below a minute. So it's an extremely quick way to start looking at what's happening on your device. But you can see that the peak power added efficiency found in this case, it's about 68%. When doing harmonic tuning, there's normally two approaches. You could, of course, start sweeping all the variables, fundamental load, second harmonic load, third harmonic load, and so on. This makes for, this makes me happy, of course, but it makes for a lot of measurements. That could take days. So what we normally do, or what our customers normally do actually, is they start optimizing all the harmonic impedances at the load and at the source in kind of in an iterative procedure, and then they re-optimize the fundamental impedance at every step. So here we fix the fundamental impedance to the peak PAE found in the previous stage, and we start finding the optimum for 2F0 on the source on the load and 3F0 on the load. And afterwards, in the final measurements, after finding the optimum of all these harmonic impedances, you sweep again the fundamental to re-optimize. So in this case, you can see that for this last measurement, the peak PAE found, it's about 86.7%. So through harmonic tuning, you have an improvement of almost 20%. And the final performance on this transistor shows well, power gain of 14 dB, GT of 10 dB, and drain efficiency of 90%. So it's interesting at this point for this optimum to start looking at what's happening at the device intrinsic plane. So here you see the voltage and the current waveforms that are de-embedded to the device intrinsic plane by well, de-embedding the output capacitance of the transistor. And over here you see the load line. So you see first thing that the peak voltage is about 3 times higher than VDD. VDD is 30 volt. The peak voltage reaches 90 volt. That's due to the non-zero phase of the second harmonic load impedance. And you see that these waveforms get close to something like class F. The very high efficiency is due, well, thanks to the low knee voltage. That's in the order of 1 or 2 volt. So essentially the same procedure was done also at X-band for an 8 by 125 micron device. So here, again, we start with a fundamental only tuning. Right here you see a contour of maximum power added efficiency in red. Obviously, now we're trying to find optimum efficiency, but you could do the same for power. So you see that the power contour is not closing in this particular measurement because we're looking for peak efficiency. But after finding this fundamental load, where we have a peak PAE of almost 60%, we start basically tuning second harmonic load and second harmonic source. The procedure is, again, fairly simple. You start by tuning second harmonic load with fundamental load at peak PAE, reaching 61.3%. After retuning fundamental, you get up to 63.4%. At that point, we start with the second harmonic source, where the other two are at the optimum, going up to 65.3%. And finally, we can retune the fundamental. And I'll show you the measurement in just a bit. One very small consideration is that each one of these measurements takes between 1 and 6 minutes. And that's why, essentially, this is done, because a full optimization would take something around half an hour. So this is the final measurement here, where you see the fundamental load sweep, second load and source. And the final performance reaches a PAE of 66%, with an output power of a little bit above 3 watt. So one other interesting possibility, well, at least if you're a device manufacturer, is to basically start using load pool in a kind of a production testing environment. That's something that today it's not really done, mainly because of the speed limitation of load pool systems. But in Freiburg, they have basically implemented a custom software to basically use the active load pool system in combination with a probe station to automatically scan complete wafers in a fully automated fashion to basically check for process variations and things like that. So over here you see an example of this final performance measured on this gallium nitride HEMT at X-band. And from these curves you can basically see that the distribution of the most important parameters, for example, the devices deliver all an output power bigger than 35 dBm, power gain bigger than 12 dBm, and PAE bigger than 65% across the whole wafer. This brings me to the conclusion, I think, in good time. I just tried to give a non-biased overview of different types of systems load pool systems that are available today. Obviously, each one of them have their own advantages and disadvantages. So in case you're looking for a load pool system, you can evaluate different solutions and check which one suits your need best. And then finally, I presented some users example of harmonic load pool investigations on gallium nitride transistors. Thank you very much for your attention at this hour.
Does anyone got any questions?
Well, this is very similar to the nonlinear vector network analyzer developed a few years ago by Agilent. Well, it's very similar because they have the ability to basically tune the load by injecting harmonics in the output.
Well, basically, if I go back to the to my initial slides, Maori microwave. Yeah, exactly. So I'm now talking as Maori microwave, which is our parent company. Maori microwave basically provides both types of active load pool solutions. So there's a vector receiver solution that's based on PNAX that is also active, but it's mainly single tone. And the mixed signal load pool is somewhat of a dedicated platform for load pool. So essentially, the two platforms can do the same, well, can do most of the same measurements. So they can measure nonlinear time domain voltage and current waveforms, both the PNX and the mixed signal load pool. They can do load pool in an active way. The main advantage of a mixed signal is that it's faster and that it can do modulated signal load pool. That's the.
Is the calibration routine the same for the polyharmonic?
Yeah. Yeah. Same calibration. So normally in a vector receiver system, that's this one. You start with a normal two-port calibration of VNAs. So ISO-LT or TRL calibration at the device reference plane. You have a power calibration that's in order to measure absolute power. And to measure time domain voltage and current, you have a phase calibration. So you use a phase reference device to, yeah.
You have a polyharmonic input source to calibrate the phases.
Yeah, you have a forget about how they call it. Well, phase reference device. So yeah.